Okay. We discussed how to calculate capacity, starting from the material properties to the analysis, non-linear analysis of the structure. We have calculated capacity, and then we also discussed how to compare the hazard with the capacity to get the performance, and an iterative method to do performance-based design, in which we will calculate performance under given hazard. That performance may be satisfactory, may not be satisfactory. If that performance is acceptable to you, the design is okay. If that performance is not acceptable to you, you have to redesign your structure with higher ratio. Okay. Or looking at the hinge pattern, you can identify that which are the members which are controlling the capacity of your structure, and if there is any premature failure, you can change that. So you get an idea about the hinge pattern. So what we look at is the hinge pattern. Okay, or failure pattern, whether the yielding is occurring in the same sequence as you desire or not. If there is any undesired sequence of hinge formation, you can change it by changing the relative strength. And then the performance point. And that performance point may be acceptable as per your target performance of the structure, or it may be unacceptable. If it is unacceptable, then you have to redesign. So we have to perform iterative design. So this process is clear. We have discussed so far. So is it okay, or you want to ask anything up till this point? We also discussed tutorial number 5. 5 we discussed. No, 5 not yet. Last class we were discussing 5 only. We have done that non-elastic response spectrum. The elastic response spectrum is part of 4. So anything you want to discuss in tutorial number 5? I have given you 3 methods of performance evaluation. Okay, what are those 3 methods? Can you recall? ATC 40 and equivalent linearization are the same. Okay, only difference is in calculation of damping. So ATC 40 equivalent linearization are the same method. So one method I have given you, equivalent linearization. ATC 40 is one of those. That other method, displacement modification method. AC as per SC 41, where you have different coefficients C0, C1, C2. Using those C0, C1, C2, you can calculate the inelastic displacement, and that gives you the performance point. Third method, constant ductility or east acceleration spectrum method. So Newmark has given the procedure to calculate the constant ductility in acceleration spectrum method. Okay. And we use that to obtain the performance point. So this is our third method. Okay. The same method is also called AERD method, inelastic displacement ratio, because the constant C1 there is nothing. What is C1 giving? So this ASC 41 method or displacement modification method, this is also called AERD. So AERD is nothing but C2. So C2 in DMM is actually AERD, inelastic displacement ratio. So there are a number of procedures available to calculate AERD. C1, yes. C1 is ideal. C0, C1, C2. So C1 is ideal. So now using that, can you solve tutorial number 5? Let's have a look. Right. Okay. So a simple capacity curve you can plot an elastoplastic capacity. So in elastic capacity curve, this is our yield ratio VVY and the corresponding value of delta. This VVY you can take as VVD into, if overstrength ratio is, you can calculate like this. And then you can calculate delta U as mu times delta. And how to calculate delta Y? Sorry? Right. So in that case, you have to consider this to obtain as per SC41. Then you have to assemble element wise. Yes, sub-assembly wise you have to assemble. Then only you can consider the member operational capacity as SC41. In linear, in code basis.
We are using the first rule, then find transformation factor, and then we are using this ratio, and then we are doing it. But then here and here, what is the difference? Here, the difference is that
Here we are calculating mu. Here we are not calculating.
but here again you are calculating mu and again calculating r, and then you are using rows.
Right.
Here r value is means
Here R value is given in code directly. That's the difference.
and here
Here R value you are calculating using the value of mu.
and that will be decided by me.
So mu is decided by
Us,
not us, not us. It is decided, it is obtained from nonlinear analysis of us.
Yes, but that delta target is decided by us now. But how much information I want in my structure?
Yes, delta target is decided by you because you are deciding a performance.
Yes.
But at that delta target, what will be the value of mu? That we can't decide. That is decided by the nonlinear analysis of that. So in this case, you will require nonlinear analysis of the structure. Here is not required.
But here, sir, while getting this mu equal to delta target upon delta y.
Yes. How to get delta y?
Delta y is getting on characteristics of material.
How?
By
How will you get delta y of a building?
delta using we calculate now by performing analysis, nonlinear analysis.
That's what I'm saying. That for obtaining delta y, you have to perform nonlinear analysis. So in the second case, and even for deciding delta target, the target displacement also, you will do nonlinear analysis because you do not know what delta target I should take. Which delta target you will take? 2%, 4%, 8%, what? Delta. So that will also be decided based on nonlinear analysis, that at which target displacement you are getting acceptable performance. So delta target will be decided based on acceptable performance. Delta y will be decided from the nonlinear analysis. So you will require nonlinear analysis.
And delta acceptable how it is
Based on performance level, whether you want IO, LS or CP. So let me explain again. This is that. For performance based design, you have to first do some preliminary design. So first preliminary design is required. Without preliminary design, so step 1 is preliminary design. This preliminary design is necessary. Without this, you can't perform performance-based design. Okay, so how to do this preliminary design? Initial design will be required, and initial design in fact is required in case of our code-based method also. But there you require only stiffness. Here, in addition to stiffness, you need ductility and strength also. You require stiffness, you require strength, and you require ductility. How it will be obtained? That you require size and reinforcement detailing of members. Then only you can perform non-movement. Okay. In code-based method, you require only size of the method. There also, for calculating time period and distribution of the forces, you need a preliminary design. But that preliminary design, you need only size. Reinforcement is not needed. Here, you need size as well as reinforcement. Then you will perform nonlinear analysis. What will this nonlinear analysis give you? This nonlinear analysis will give you a capacity curve. And on this capacity curve, you will get IO, you will get LS, and you will get C. Okay. Now you will do two things. First, you will decide your performance point. Okay, that means the target displacement. This displacement your target, and this you will decide based on whether you want IO, LS or C, where you want. And then by linearizing this, you will get delta Y. Then you know delta T.
Sir, the elastic analysis, the response reduction factor we are using is like any range falling between in those displacement.
Sorry, I couldn't get. Can you repeat? In
the response reduction factor
in code.
In code or in elastic design.
In code, there is a fixed value of response reduction factor given for one type of building.
One type of building.
You will take that value.
Here we are deriving that response reduction.
Here we will be calculating R xi or R mu, which is function of this ductility. So you decide how much damage you want. Okay, and the building capacity curve will decide what is value of delta Y. That will give you the mu. From that you will calculate R xi, and then calculate dVy and design for V. How you will calculate dVy? Once mu, delta T, R xi is known, how to calculate dVy? Horizontal acceleration. And how to get horizontal acceleration? But how will you get period? Period for the building which you are going to design. You have to find out that. Not the period of this building. Not the period of the building which is being designed in the code. Period of the building which you are designing. How? That's the question. But that is an empirical formula for elastic period. Okay, in the elastic. And that is empirical formula. Okay, that may not be true. That may not be true for my building. Yes. But this formula is not same. The period here is not same as the empirical formula given in the code. We have seen even when you are doing correction, PV bar by PV you are doing, that comes out to be 2.5. So empirical formula is giving us much smaller period than what you are getting from us. So the period of my building which I am designing is not going to be the one which is given in the code.
We will convert this multi-degree freedom system into single degree freedom system.
Okay. Then
by considering single degree system is now, so considering it as in fundamental mode, it is depicting in one like cantilever. For cantilever can calculate cantilever by
how?
EI to open to EI by.
But I do not know EI. I am here to design my building.
But EI will get from that capacity curve,
that will be of the preliminary design. Okay.
We have to go for iterations.
You have to calculate which period you should design for. So, for that what you have to do, you plot SD versus T for xi equivalent. Xi equivalent you have already calculated, or reducing by R xi, you will calculate SD versus T, and then whatever is the target spectral displacement. This SDT is what? Delta T divided by gamma 1 phi. So that will give you SDT. Corresponding to this, you can calculate T equivalent. This is the equivalent period for which you have to design. Okay. And if you assume let us say the building which you are going to design, it is having idealized capacity curve like this. This is delta T, this is delta Y, this is our K equivalent. So this K equivalent will be equal to M equivalent into omega square. So that is 4 pi square divided by T equivalent, which you have read from this. And then you can calculate this du by as and this is the base area for which you have to design. Yes.
will be 6 made of by building which are considered concrete.
Yes, we are assuming here also there are certain assumptions. We are assuming that there is not much change in the mode shape of the preliminary building and the building which you will be designing. There won't be much change. There can be change in the period, but in the mode shape, the change will be less. That is one assumption. Okay. So, using that, you can convert, if the mode shape is same, you can convert delta T into SDT. Similarly, the mass participation will be same. The weight of the total building will be more or less same. Okay. If you are increasing columns a little bit, you may, or maybe you are not increasing the column, you are increasing the reinforcement, so weight will not be affected much. So these are the things. Okay, so like that you can design. What is the problem? I mean, basic difficulty you are finding. The basic difficulty here is that there has to be a preliminary design. Initially some design has to be there. And how quickly it will converge to the correct design, that will depend upon the preliminary design of the building. Okay, so there is a method, what we call Priestley and his group developed this method, what we call direct displacement based design. In short, we call it DDB. So you can use it to avoid preliminary design, or you can use this design as a preliminary design and then cross check the performance using the method we have decided. Okay, you can treat this itself as a preliminary design, so it will give you a very good estimate of the design of the structure or the base shear of the structure for which you should design. It will give you a good estimate of that to get the targeted performance. Okay, what are the requirements, prerequisites to this? So first prerequisite is that the performance point in terms of inter-story drift ratio. It cannot consider performance point in terms of IOLSCP. It will consider performance point in terms of inter-story drift ratio. Okay. So, for example, we can say that, let us say IO corresponding to 1% inter-story drift, life safety corresponding to 2% inter-story drift, and collapse prevention corresponding to 4% inter-story drift. Or you can decide any inter-story drift yourself. Suppose you decide that I will design for 3% inter-story drift. Okay. So this is first requirement. How you will decide inter-story drift in advance? Based on the performance of previously designed buildings. Okay. So generally the buildings collapse, RCC buildings collapse at 4%. Okay. So you should not take drift more than 4%. So if you are accepting damage, you are accepting the building just at the verge of collapse, then you can take up to 4%. If you want to have better performance, go for lower interest rate. So this is the limitation or prerequisite of this method, that performance point should be defined in terms of interest rate. Secondly, either mu or delta y. Should be known. So either you decide that this much is the ductility ratio which your structure can provide, or you have to estimate delta y something. Okay, then rest of the procedure will be same as I have discussed earlier. What will you do? Once these two things are known, then steps will be that first you will calculate xi equivalent from mu. If mu is not given, delta y is given, then you will calculate mu as a delta target divided by delta y. If mu is given directly, you can use that mu to calculate xi equivalent. Then you calculate r xi from xi equivalent and develop SD inelastic versus T spectrum. You have to simply divide SD elastic, which you know, by Rz. Then you read T equivalent from SD elastic versus T plot for delta T or delta D, whatever you want to call it. Then once this T equivalent is known, then you can calculate K equivalent as SD equivalent or SDT SD inelastic corresponding to T into SD by omega square into 4 pi square
Plot for delta T is what?
plot for
Delta T.
delta
That's good. Read T equivalent on SD
as being elastic versus T.
and then plot for delta T.
SD versus T, this is the plot, and delta T is the target displacement corresponding to which you are reading. Okay, what is this? Normal, let us say you are designing in zone 5, you can plot SDE versus T. This is for xi equal to 5%, mu equal to 1. This is our demand curve, original. Okay, we can plot it for any value of mu or xi by reducing it by R5. Now this you have to read for T equivalent corresponding to the value of SD, okay, inelastic, or SDT or delta T, whatever you are calling. This will give you T equivalent. This is the spectral displacement for which you are designing, which you have decided in your beginning. For that you will read T equivalent. Okay. Once you know T equivalent, then you calculate K equivalent like this. Yes. T equivalent is equivalent to secant. M omega square. Yes. So now SD. I'm sorry. This is the M. K is M omega square. Not SA. I have calculated SA. So we are not calculating SA. We have already obtained T. We can calculate M equivalent. What is M equivalent? Mass of equivalent single degree freedom system into omega square, that is 4 pi square by T equivalent. Okay. Please correct in the previous slide. I think there also I have written SD into, that is SA. Sorry? This I have to obtain from the building. Suppose I have a 10-story building. I have to convert that 10-story building into equivalent single degree freedom system. How do we convert into equivalent single degree freedom system? The mass of the 10-story building divided by alpha 1, and alpha 1 is summation mi phi I whole square divided by summation mi phi I square. Modal mass. Equivalent single degree freedom is the modal mass as per that particular motion which you have considered. So this gives you K equivalent, and once you get K equivalent, you can calculate VVy as K equivalent into delta T, target or design. Both subscripts you will find delta T or delta T, design. Yes. To read, not that capacity we are doing. Problem is that this response spectrum, this is for single degree freedom system.
Yes, in the demand we have to choose for the target displacement.
The demand we have to yes,
For the target displacement, but for the VP line we have to calculate from the K equivalent. That means over K equivalent is the 10-story building converted into the single degree freedom system.
Right.
From that capacity we have to match with that displacement.
Right.
For the K equivalent we have to.
For reading the response spectrum, we have to convert this into equivalent single degree freedom system. So wherever we will be reading response spectrum, it is must to convert that into equivalent single degree freedom system. That's why we are converting it into equivalent. Once we know now T, then we can calculate K equivalent. Now we can calculate the base shear of the original building.
Sir, this delta target is inelastic displacement.
Total displacement.
Total displacement
Which you want.
which I want, but that is in inelastic range. That is after input.
Right.
Then how this P equal to K delta is varying?
P equal to?
P equal to K delta is VBY you are calculating. VBY equal to K into L.
That's what I plotted now. I plotted this earlier also. So this is VV versus delta root. This is delta T
Yes.
and this is K equivalent and this is VVy. So you can see that this is the line joining. So slope of this multiplied by this displacement will give you this value. Assumption here is that alpha is J. It is elastic, perfectly plastic. If alpha is non-zero, then also you can do, but in that case you should know the value of alpha. Then you can calculate PV by then also, but you should know the value of alpha. Post yield stiffness. So it will relate, if you recall, if the curve post yield is not flat, it is like this. So this is K, this is alpha K, and then suppose this is delta T, this will be your K equivalent, and this will be your value of VVY. If you want to compute VVY now, you need to know the value of K and alpha. Okay, or alpha at least. Then K equivalent and alpha, if you know, you can calculate this using geometry. The equivalent single degree freedom system of a non-linear multi-degree freedom system will also be non-linear. So the non-linear multi-story building I have converted into equivalent non-linear single degree freedom system. So my single degree freedom system is also non-linear, such that their initial periods are same, okay, mu is same, and hence their equivalent periods are same. The single degree freedom system has been converted in such a way that the initial period was same. Okay, yield displacement is we can calculate by the relationship between SD and delta. Okay, so initial period is same, ductility ratio is same, and the equivalent period, secant period, is also same. And then its properties are related with the multi-degree freedom system through motion. Yes. It is secant period. This is our multi-story building. We have considered a particular node shape, okay, and we have obtained VV versus delta. This curve we have obtained. Okay, this is our multi-degree freedom system, and this is the capacity of this multi-degree freedom system. I am converting this into an equivalent single degree system. This equivalent single degree freedom system has TE same as the TE here. Okay, and equivalent you can calculate from mode shape, modal mass. Okay, you can calculate this equivalent height as well. Okay, what will be the height so that you get the same rotation and same moment as this, and then its displacement here, this will be SD. Here it was delta roof, here it has become SD. Relationship between SD and delta roof also you know. Okay, and its capacity curve will be given in terms of SA versus SD, which will be similar. But this will be SA in place of base shear, this will be SD in terms of delta. Relationship between them, you know, and this actually the slope here is not giving us TE, the slope is giving us KE and K equivalent. And here this slope is depending on T. Slope is not T, remember? And this will give us T equivalent. So this is the original structure. This is the corresponding single equilibrium system. We will be switching over between these two, from here to here and here to here, using some simple relationships, and those relationships are that this M equivalent is how much?
This switching from multi-degree freedom system to single degree freedom system, we are doing just to take the benefit that we can use the response spectrum.
Because response spectrum is in terms of single degree.
That's it.
If we are not doing that, we can't read the response from single degree freedom. Sorry, from response spectrum. So that we are able to use response spectrum to represent earthquake, we have to do this.
Can we say that it is a whatever displacement we are getting from multi-degree system actual, and then we are converting them into single degree freedom system. These are the actual, means there will be no difference after
Those will be related.
Yes.
Okay, and that relationship is, you already know that SD is delta 2 divided by gamma 1 phi 1 or gamma, because here I am not saying that this is first mode or what mode, so just mode, so gamma into phi.
So while converting this from multi-degree to single degree, you are considering only that K equivalent is KE, not K equivalent. For taking this time value TE, you are considering initial stiffness KE. You are considering K equivalent now.
Same relationship will be between KE and TE and K equivalent and T equivalent. Same relationship will be available here also.
And
So, for example, KE is M equivalent 4 pi square by T square, and K equivalent is M equivalent into T equivalent. Sorry, 4 pi square divided by T equivalent square. So, same relationship is valid for between K equivalent and T equivalent.
we are considering for response spectrum first mode.
Response spectrum is for single degree freedom.
Single degree system.
We are considering a mode from here to here. Now that mode will be first mode, but first mode is representing elastic behavior.
Yes.
So there is an assumption that we are assuming that the mode shape remains same, but that is not true. So I will give you later. Okay, Priestley has derived that in case of inelastic structure, what should be in case of a multi-story building which is inelastic, what should be this mode shape, which takes into account the inelastic deformation. So that will not be exactly first mode, it will be a combination of some modes, but whatever the shape you have decided, which you think will be the deformed shape during earthquake, using that shape you can convert your multi-degree freedom system to single degree. If nothing else is given, you can take first mode, fundamental, which is having maximum participation.
Which is that to get mass equivalent, you are considering this mass equivalent considering model parameters.
Right.
But we are considering already first mode.
No, I have not written any first or second here. No? I deleted this. So I have not written one. So whatever mode shape you have chosen, whatever deformed shape you have chosen, that I am representing by phi.
But while taking time period from the stiffness by mass, we are considering mass. That mass is the whole mass of that building or of the structure. And here we are
For calculating period.
time period.
No? Period comes from the analysis of either multi-story building or analysis of single degree freedom system. Both are same. So this mass and stiffness will be such that here also you get the same period and here also you get the same. So mass of the two and stiffness of the two are related in such a way that both should have same period. Okay? Yes. Performance-based design can be done using time history. Performance-based design can be done using response spectrum. Because it will depend how you are representing your demand. You can say that I want to design for this time. Okay? Or I want to design for this set of time. Wait. Then this single degree freedom system business is not needed at all. Why we need single degree converted into single degree freedom system? When your demand or hazard is given in terms of response spectrum. Okay, because response spectrum is for single degree freedom system. So in some way you have to convert your actual structure, whatever that structure may be. It is building. Sometimes it can be just a bridge pier, which itself is like a single degree freedom system. So whatever your structure is, you have to present it in terms of a single degree freedom system. If you want to use hazard in terms of response spectrum. If the demand is given in terms of response spectrum, not in terms of ground motion. If it is ground motion, then all this is not needed. I will tell you later. You can analyze for the ground motion directly. Then conversion into single degree freedom system is not needed. It is to be able to use response spectrum. So because most of the times the demand or the hazard will be available in terms of response spectrum. So to read response spectrum here, we need to convert it into equivalent single degree freedom system. If I want to read it. Yes. Only thing is that now we are using it to do the preliminary design of the building. That method can be done to obtain performance point of a structure which is given to you. Here, when we are designing the structure, it is not given to us. We are trying to design the structure. What is given to us? These prerequisites. These are given to us. Rather than giving the structure, see, one problem is of analysis, another is problem of design. In analysis, what we are doing, the building, everything, all the drawings of the building are given to you. Then you can make its model and you can calculate its performance. That is the problem of evaluation of performance of a building which is already either existing or has been designed. That is one problem. That part is finished. Now we are moving to the second part. I want to design a new building and I have decided that that building I want to design for a particular performance level. How to start with? So one way would have been that you design any random building by any method, check its performance. If that performance is okay, be happy. If not, do iterations. Go on doing iterations till you are happy. That is one way. What I am trying to tell you is how to minimize this number of items. So DDVD is one method where you can achieve a building from scratch. Nothing is known. You can achieve a building which is close to your target building quickly.
The first example of the view of this building and the industry drift, we have to take an account for the new building design.
So you have to decide when you want to design a building, these two things you have to decide.
To match that performance.
So the building which you want to design, you have to decide these things. And how you will decide? That will be based on your past experience. Okay? Yeah, come on. Yes. So once you do that, once By is known, then what you have to do is design the building for Bby. How to design for Bby? In the same way as for BB bar in code based design. But taking expected material strength and partial factors of safety equal to 1. So design for BBY is same as you do design for BBY. You perform an analysis of the building, you scale it to BBY earlier, now you scale it to BBY. But design will be done taking expected material strength FCK plus 1.64 sigma, Fy plus 1.64 sigma, okay, in place of FCK and Fy, and partial factors of safety gamma equal to 1. Because you are doing this for BBY, you will get the yield strength as this. Okay, so this will give you a closed design of what you want. Okay, what industrial drift you have desired, what ductility ratio you have desired, it will give you a design closed. Then you check it as in iterative method. If it is fine, okay, otherwise no more iterations. So this method is to reduce the number of items. Otherwise you can start with any building and you can achieve, you will get some performance. That performance may be far away than what you have done, and you will go on changing it, number of iterations, and these number of iterations are to be done with non-linear analysis again and again. So that will be very costly. Performing non-linear analysis will be very difficult, very costly. That's why we are doing this. Okay, so today's class I will stop here.